Et maintenant, nous allons accueillir le professeur Robert KAITA, qui lui va nous ramener à la physique quantique. Alors le programme est un peu différent parce qu'Éric Geoffroy, qui était prévu, sera là tout à l'heure, rassurez-vous. Il est arrivé de Dubaï dans la nuit, donc il se repose. Là, il devait être à Dubaï hier soir, c'est un imprévu. Donc il sera là, donc on intervertit le programme. Il va parler à la place du professeur Robert KAITA. Le professeur Robert KAITA est un physicien nucléaire de la fameuse université de Princeton. Il travaille donc sur cette source d'énergie potentielle très importante pour l'humanité de fusion nucléaire. Mais là, il va nous parler de physique quantique et de spiritualité. Robert KAITA. Ah, pardon, oui. Excusez-moi, j'ai zappé notre ami Luc qui avait des dessins à faire. So we look at Luc Tesson first. Ah voilà, ça c'est très très bien. On va vers plus de complexité depuis le Big Bang. On est bien d'accord, Luc. Absolument. Ensuite, ben oui, c'est ça. Hein. C'est difficile de trouver une loi universelle quand on regarde l'origine de la vie. Oui, ça aussi, c'est une bonne illustration de ce que Paul nous a dit. Hein, on ne peut pas passer de la brouette à la fusée par une succession de heureux hasards. Et ensuite, c'est bon, et ben voilà. Merci Luc, et merci, on applaudit Luc. Et donc, Robert, your turn.
Okay, my turn.
You have,
Yeah. Okay.
control here.
Okay, well, that's fine. Well, thank you very much for the very kind invitation to speak here before you today. The hospitality has been wonderful, and maybe my only complaint is that there's been too much good food that I've been eating during my time here. So today what I'll be talking about is quantum mechanics and faith in things unseen. And so I would like to begin with an introduction. This is my outline. I will be talking a little bit about the atomic model and something called probability amplitudes, which were alluded to earlier in this symposium. And then talk a little bit about quantum mechanics and its implications for what we might call reality, and compare it with a classical sense of what reality means. And then re-envisioning the rationality of faith within that context of a reality that's no longer restricted scientifically to the material world, and then a summary. So then, starting with an introduction, I wanted to start this way because some years ago, a student of mine who went on to become a professor at another institution said that it was their custom to list their academic ancestors. And I didn't think much about it, but I said, I'll try and see how far I can trace our collective academic ancestors. And so there's me at the bottom, and my advisor, Charlie Glashauser, and his advisor, Ruby Sher, who had a big role in the development of nuclear weapons, frankly, in the Manhattan Project, and then Henry Smythe, who in the United States has quite a reputation for writing this famous Smythe report about the military uses of nuclear weapons. And here it gets kind of interesting because he went to Cambridge and studied under Ernest Rutherford, who discovered the atomic nucleus, who in turn was a student of J.J. Thomson, who discovered the electron. So if I make any mistakes, if there are any errors in my presentation, it's not because of my academic ancestry, but solely my own fault. So then, now talking about the atomic model and probability amplitudes, we'll look at then what we call the planetary model of the atom. And this, thanks to Jean, I should put an X through it because it's incorrect. Now, I felt a little bit self-conscious about this because everybody, and I include scientists and engineers, love to depict the atomic model in terms of something that looks planetary. And I'm sure many of you in the audience who aren't professional scientists immediately can sketch or recognize something that has a nucleus in the middle and electrons orbiting around it. First of all, the scales are absolutely wrong. You couldn't even see, if this model were in any way correct, you couldn't even see the atomic nucleus. But it has become very much a part of our popular culture. But as we heard earlier in this symposium, there are certain problems with this kind of model that is called the planetary model because, in fact, after J.J. Thomson discovered the electron and Ernest Rutherford did experiments to find out that then there was a nucleus, a very heavy nucleus with most of the mass right in the center of the atom, that then this would be an appropriate model, but there are problems. The electrons orbiting the nucleus would be accelerating and give off energy. And we know this from your popular common experience in that we have radio waves. We connect an antenna to a power supply, and then you accelerate the electrons up and down, and what they do is they generate radio waves. And eventually, if this model were correct in the classical sense, the electrons would spin into the nucleus. However, there was then experimental evidence that somehow electrons were somehow outside of the nucleus was in the center, and it was in something that people would call an orbit. So then, there was somebody who, the German physicist Schrödinger in 1926 says, well, let's think of electrons instead of particles moving around as waves. And here I'm doing some higher mathematics, which is for the purposes of this illustration, let's start with an orbit. It's a circle. So doing higher mathematics, we unravel the circle into a line, 2 pi r, where r represents the orbit of the electron. Now then we go to, now suppose, once again, that instead of thinking of particle as an electron as a particle, let's think of it as a wave. Now, in that sense, we want to have this wave constrained. The wave must not be too big. Then we'd go, maybe this doesn't show too well. But anyway, if it's too big, the wave is just simply too long for that line that would correspond to the orbit. If it was too small, it wouldn't fit either, because it would be not long enough to then go ahead and then fit in that orbit. But if it's just right, it will just fit. And so we have here a connection between a wave that represents the electron and the orbit we find it. So, I apologize for how this slide turned out. But anyway, what happened was that what it was supposed to illustrate is that over on the first end, what you'd find is that those lines, here. Yeah, what was supposed to have happened was that if it was too big, you'd find this then orbit looking like that. And if it was too small, the orbit would look like this. And again, I apologize how I was translated into this slide. But instead, if it's just right, it's just going to fit into that orbit. Now, here's the part that's very difficult to conceptualize. We're not talking about, in quotes, real waves, although they have an analogy to what people classically thought of as being waves like water waves, or the waves that you get when you oscillate a string that's connected to one end on a jump rope, for example. But instead, they correspond to something called probabilities. In other words, if it's too big, the probability of that wave fitting into that orbit is 0. If it's too small, the probability is similarly 0. But if it's just right, if the probability is 1, if it fits, then the probability is 1, and it fits right into that orbit. And so this gives you a flavor of what we call quantum mechanics and quantization. In other words, if it was true that a planetary model would work, even forgetting about the idea that an electron wouldn't be stable and staying there like planets in orbits, what will happen is that according to quantum mechanics and according to observations of the energies of the electrons, they couldn't in any way occupy any orbits that do not correspond to allowable orbits. They are quantized because the probabilities, according to this model, the probabilities would simply be 0. And so that's why you would have these electrons in very specific quantized orbits. Not continuous, but quantized orbits. And that is a quick introduction to the concept of quantum mechanics and the origin of the term. So now, let's look at quantum mechanics and what I would call reality. Now, quantum mechanics and the new reality, in my estimation or my summary, would be like the following. Quantum mechanics allows you to calculate the probability amplitudes, but are not measurable in themselves. You don't measure probabilities. Probabilities are numbers that tell you whether something is very probable or not probable. So here's something that's very strange. You have something that tells you where things are and leads to measurable quantities, but technically speaking, are not measurable in themselves. They are not quantities in the traditional sense of something you can measure, like a line, for example. These probability amplitudes give you measurable locations of electrons and other subatomic particles, or give you measurable information about them. And for this reason, one way to think about this is that probability amplitudes can thus represent the way science allows non-measurable reality because they lead to a measurable reality. And this is the first time that such a creature, such a formulation of science appeared. And this was unknown until the time that then people started exploring, starting from my academic ancestors, the fact that there are subatomic particles. The atomic model looked fine all the way up to the etymology of it, the word atom itself, from the Greeks. Indivisible particles that would then go ahead and build up the previous classical view of reality. But once you started probing and discovering that there were these subatomic particles and the way they behaved, it then leads to this kind of new, if you will, new concept of reality. Now, this has some implications in something that has been alluded to earlier in this symposium, but I think that we should look at this carefully, because people who are familiar with this famous example of Schrodinger's cat focus more on paradoxes. Like, if you set up this experiment, is the cat alive or dead unless you do the measurement? But what I would like to do is to then focus on the setup of the experiment itself and the implications of what it says about reality in its totality. So what I'm going to say is the following. There's this experiment where then you take a box. It is a box. In principle, I could do this on the stage here. Maybe I really don't want to do it on the stage here. But I might want to do the experiment where I bring out a box. And that's a box. There's no doubt about it. You can see the box. No question about reality in the classical sense. Now, inside the box, I stick this poor cat. Again, it's a real cat. You can observe the cat. No ambiguity there. In the classical sense, it's a cat. You put it into the box. You can stroke the cat, give it a bowl of milk, you know, so it stays there. No problem there. Then you have this radioisotope. You could use uranium, for example, because, in fact, that was the radioisotope that Rutherford, my academic ancestor, used to then generate these particles, or use it as a source of these so-called particles. They didn't know what they were, so they called them alpha particles. These particles that are emitted in a probabilistic, statistical way that, you know, you can't tell whether any one particular atom is going to then, a uranium atom is going to spit out an alpha particle, but in a collection of them, statistically, there's a chance that these alpha particles are going to come out. So again, no problem there. You stick this uranium inside the box. And then all the other mechanisms, as illustrated here, are very real. You could have hammers. You could have that terrible bottle with the poison gas in it, and the Geiger counter. In fact, the Geiger counter was named after Hans Geiger, who was, in fact, one of Rutherford's assistants, who had the tedious job of sitting there and counting these particles as they come out. And so all of these are real objects. Now, then it goes on to then people go ahead and talk, and there's nothing wrong with this, to talk about the real state of the cat is determined when the box is open. And here it becomes a question that's interesting to me. The question is whether the cat is still real when the state of the box is not known prior to the opening of the box. And I think it's important because of the following implications for reality, let alone the paradox of not knowing the state of the cat. Because if you then look at here as an implication for why quantum mechanics suggests limits of scientific knowledge, let's think of it this way. We have an initial state, Schrödinger's cat outside the box that I just mentioned. The state is observable and known. And there's no question, classically, that this is scientifically real. Now, if, and this is the big if you think then that reality is solely dependent on that which is measurable, you have a very peculiar situation here, because you have the real cat that then goes into an intermediate state where you put the cat in the box in this experiment. And everybody talks about the paradox. You don't know whether the cat is alive or dead because you don't know whether the time that the cat is in there, that an alpha particle decays, hits the Geiger counter triggers the hammer falls, and then smashes the bottle of gas, and then kills the cat. If you're, and I can't emphasize this enough, if you think that the reality is only dependent on that which is measurable, you get into a very bizarre kind of, not, I should say bizarre, but something that you have to also deal with intellectually, because you go from an initial state, which is real, no question about it, and the classical people would say, yes, that's real, into this intermediate state, which is a consequence of the quantum mechanics having to do with the statistical probabilistic decay of the radioisotope, and the fact that you don't know the state, that suddenly then the cat becomes real, unreal, and then back to become real again when you go ahead and you open the box. And there is an observation of the final state of the cat, living or dead. Now here's the thing. Because of what quantum mechanics says about this particular experiment, it is equally rational for me to believe that reality includes the reality of the cat that we all agree on before we start the experiment. I conclude that even though I don't, in quotes, know and visualize and can determine the state of the cat in the box, I can still say that it is equally rational to think then that the whole system embodies a reality that I can't see. And then the final state, which we all agree on, we can see. So if you're absolutely adamant about saying that material reality is only that which you can observe, you have that choice of saying you have a cat that goes from reality to non-reality to reality. And I say it's equally rational to then say all of these represent reality, even though in this state you're not seeing, if you will, in the materialist sense, the reality of the cat. So now, what does it say about what I would call re-envisioning faith? Now, there is a book in the New Testament, as a Christian, that I consider a very important text for my faith, that has a very interesting phrase in there. In the 13th chapter of the letter to the Hebrews in the New Testament, it begins as follows. Now, faith, and the faith we're talking about, is in the faith in God, is being sure of what we hope for and certain of what we do not see. And then it goes on to then go ahead and give examples from the great prophets, the great people of all the Abrahamic faiths. They say that the subsequent illustrations all contain observables. These are all observable events that follow from that verse. The creation of the universe and the faith-based acts of Noah, Abraham, and Moses, and many others that are described there. So, what does that say? We can, in a very rough way, set up the same kind of syllogism or argument or train of logic that then follows from now this broader view that quantum mechanical thinking allows us to have. So what? We have an initial state. Abraham lives in Mesopotamia. That's an observable condition. If you were living in Mesopotamia, you could say, hello, Mr. Abraham, how are you? You can observe that person. Then, for some reason, Abraham is then called to go. This is a state determined by, in his belief and in my belief, a state determined by the unobservable and statistically unknowable God, whose reality can be rationally believed in. Because we have now this permissible, scientifically, view of reality that goes beyond that which is strictly observable. Now, of course, you could say that there were other reasons why Abraham wanted to leave, but it does not mean that this kind of faith is irrational or somehow scientifically excluded. And then you end up in the final state, again observable, that Abraham ends up in Canaan. The state is observable again and known, and is thus scientifically real. Now, here's then my take on the relationships of quantum mechanics and faith. So you have a potential conceptual similarity between these invisible probability amplitudes and faith of ancients in unseen leading to seen. Now, here's another factor that should be emphasized, that quantum mechanics for the first time is controversial, in quotes, because it is the first theory that necessitates interpretation. That's why there are all these debates that you got a sense of from the earlier presentations today, why this leads to so much discussion. The necessity of interpretation in quantum mechanics allows faith in God in itself to be among the possible rational explanations in the sense of what I was just talking about for the observable and real actions of the ancients. This is not a proof for God, but it indicates that it is rational. It is not scientifically excluded to then say this kind of agency of God working in these people's lives is scientifically excluded. Now, the thing is, the truths of, and there is a connection now between then science and faith in the following sense. The truths of religions that acknowledge observable historical personages, all the Abrahamic religions, that acknowledge the observable historical personage and events can still be challenged scientifically by examining the accuracy of their accounts. So in that sense, it is connected with a traditional view of reality. The rationality of believing in such religions, however, can no longer be questioned with the claim that only reality explainable by science in the material sense can exist. You can't dismiss it all by saying, oh, it's a fiction because you can't observe it, you can't measure it, because of what quantum mechanics introduces. So, summary, right? And so then the summary is that meaning from transcendent faith is thus no longer logically excluded as irrational. Quantum mechanics suggests that rationality of belief in something that is intrinsically invisible but with real consequences is rational, and the necessity of interpretation introduced by quantum mechanics means that believing in God as motivating real events is as rational as any other explanation. Thank you.